Hello everyone, welcome to our workshop EmergencyComm 2020. This workshop is in conjunction with the EAI SecureComm 2020 conference. My name is Shahriar Badsha, one of the co-chairs of this workshop. I'm an assistant professor at the University of Nevada, Reno. So let us start our workshop today. We really thank everyone involved in this workshop who helped each other to make this workshop successful today. Firstly, I want to thank to the workshop chairs, Dr. Shamik Sengupta, Dr. Charles Kamhua, and Dr. Laurent Angelia. And also, I'd like to thank all the steering committee members, Dr. Abdurrahman bin Shahid, and also Dr. George Kamhua and Dr. Tawhidul Alam. And last but not the least, I really would like to extend my gratitude and the thanks to all the other committee members and technical program committee members of this workshop. So in total, we had 8 paper submission, and among them we accepted 3 very high quality papers. So let us welcome to our keynote speaker today. Our keynote speaker is Dr. Paul Ratazzi. This is his short bio. Dr. Paul Ratazzi received his BS in Electrical Engineering from Rensselaer Polytechnic Institute in 1987, MS in Electrical Engineering from Syracuse University in 1992, MS in Management from Rensselaer in 2006, and PhD in Electrical and Computer Engineering from Syracuse in 2016. Currently, Dr. Ratazzi is a technical advisor to the Air Force Research Laboratory's Information Exploitation and Operations Division in Rome, New York. In this position, he is the senior advisor to the division chief, where he provides oversight and direction to the division's portfolio spanning interests in cyber agile and resilient architectures and systems, automation of cyber operations, cyber vulnerability analysis, system survivability, cyberspace effects generation, cyberspace SIGINT integration, multi-sensors data processing for signal intelligence, and automation of coordinated multi-domain signal and signature exploitation. Dr. Ratazzi is a senior member of IEEE and past chair of the Mohawk Valley section. So we are really honored to have Dr. Ratazzi with us today for his valuable keynote speech. And after the keynote speech, we'll start our paper presentation. Again, we really like to thank all the authors for their submissions and all the members involved in this workshop. And last but not the least, I would really like to thank the main conference SecureComm and their committee members and chairs to actually host our workshop. So welcome everyone. Let's get started. Thank you for your time.
Greetings, EmergencyComm 2020, authors and participants. My name is Paul Ratazzi from the United States Air Force Research Laboratory in Rome, New York. It is my honor and pleasure to give the keynote address for the workshop. I wish to thank the chairs and steering committee for their hard work in putting the workshop together. And I'd like to especially thank my colleague, Dr. Laurent Najila, for inviting me to present the keynote. Today I'd like to talk about mission assurance. What does mission assurance mean? How can it help us through times of emergency without throwing security completely out the window? Before I get started, I wanted to share a bit about my organization and professional perspective so that you can better understand where some of the things I'm going to talk about are coming from. The Information Directorate of Air Force Research Laboratory is located in Rome, New York. Rome is in upstate New York, far, far away from the bright lights and bustle of New York City. In Rome, we have a 65-acre campus on a former Air Force base. We also have two interesting field sites that I'd like to mention, one in Newport, New York, and one in Stockbridge, New York. I'd like to mention these in more detail because of the relationship to the topic at hand. Our Newport research site, also known as the home of the Upside Down Air Force, allows us to make antenna measurements on aircraft without having to fly the aircraft around in patterns, using up fuel, and placing pilots at risk. The site is composed of two adjacent hills, separated by a deep valley. This geographic arrangement allows us to make antenna measurements in an area that's comparable to those that we would make in a free space environment. Our Stockbridge research site has also had a history of making antenna measurements and has been designed for antenna measurements on large aircraft and large vehicles. Today, our Stockbridge site allows us to conduct experiments with unmanned systems, both aerial and ground, in a variety of environmental conditions with controllable threats. We call this our contested environment. Stockbridge has a small UAS airfield and a number of various research sites throughout the wooded area and field area for conducting networked experiments. The division I work for focuses on information exploitation and information operations. The technology we develop operates at the convergence of signals intelligence, sensor data processing, and cyberspace. Everything we do is driven by the mission of the Air Force to fly, fight, and win in air, space, and cyberspace. For the technology that we developed, this means making sure it will function in as many environments and use cases as possible. Unfortunately, many of the traditional means of systems assurance don't support this bottom line very well. This is really the subject of my talk. I'll start off by talking about how sometimes even systems with assurance guarantees or certifications will still fail when we put them in certain environments or rely on them for novel missions or unique applications that weren't thought about during the design phases. I'll point out some limitations of the traditional notions of information assurance and how the mission assurance concept can address these. I'll finish by describing a case study that we undertook at the Information Directorate to experiment with implementation of various mission assurance concepts. Whenever we design a system, we rely on many assumptions. Assumptions about the environment, use cases, the end user, the threat, etc. We have both deliberate as well as implicit assumptions that we don't even really know about. Sometimes we make assumptions regarding incomplete or poorly specified requirements. Most of the time, these assumptions err on the side of economy. This is especially true when we're talking about security and privacy. In those cases, we don't usually want to add things that aren't specifically required by the acquisition documents or nominal use cases. For most of the time, the assumptions used for a well-designed system are valid. The system operates as the designers intended, and if there were any implicit assumptions, they are still valid, even if not known, during functional testing, so everything's fine. However, when a system is used in an unexpected environment, or in the face of an emergency, or even a determined attacker, many of these assumptions can become invalid very quickly. Some common environments where assumptions become invalid are when we are experiencing periods of degraded connectivity, slow or intermittent connections. When we're exposed to a contested environment, in other words, attacks on the computing infrastructure. And finally, in emergencies, where we have possibly untrained operators or even radically different use cases that a system is suddenly thrust into. Degraded connectivity can reduce normally functioning devices to completely useless if they are dependent on persistent connections or cloud services. One example is my GPS watch, which became completely useless this summer during a several-week outage of the company's servers. Other architectures assume high bandwidth and must require constant state. Thus, they will not operate well or at all on slow connections. An example might be a company VPN service. Protocols that do not support communication delays will fail if latency is suddenly introduced into the network during an outage, during an emergency, or under an attack. And finally, many designs seem to have an all-or-nothing mentality, rather than one that values graceful degradation and partial functionality. Systems designed under an assumption of a benign environment will fail when placed in a contested one. Protocols, and even the very system itself, are many times designed under the assumption of an inadequate threat model, or even no threat model at all. Many of the Internet protocols of today were designed 50 years ago without a lot of thought given to threats. While we secure them today, we still fall into the trap of assuming the adversary thinks like us and will attack like we would attack. Finally, when we do start thinking about assuring our systems, we focus more on achieving high levels of trust, possibly at great expense, without really understanding whether these security features and gadgets really address the assumptions that we fail to account for. Emergency situations, such as natural disasters, widespread infrastructure failure, and as we now know all too well, global pandemics, can cause many important assumptions about system operation to go right out the window. Systems are suddenly thrust into environments and put in use cases that were never imagined by the designers. Failure of supporting infrastructure can result in degraded connectivity or the unavailability of critical system components such as cloud-hosted services. Finally, events such as a global pandemic can stress, to the point of failure, infrastructure and services that were assumed to be used on a part-time basis or at partial capacity. I'm thinking of a remote access service that was originally designed based on an assumption of a 15% teleworkforce suddenly being asked to support 100% of the workforce teleworking. From here on out, I'd like to focus in on cybersecurity aspects of system design. So with all these problems that come up when degraded connectivity, contested environments, and emergencies wreak havoc on our design assumptions, what can we do? Usually, for security, we apply increasing amounts of assurance through application of the three tenets of information assurance: confidentiality, integrity, and availability, which over many years of development and research have the promise of making our system an assured system. We complete IA checklists, institute security best practices, assemble trusted components into so-called trusted systems. But in the end, have we really addressed the conditions that will prevail in a contested or degraded environment or in an emergency? Not entirely. In fact, we may have made things even worse. For example, 2 or 3 factor authentication is great, very secure, and may be fine under normal circumstances. But the additional time and steps to authenticate could result in disaster in an emergency where time is of the essence. Likewise, each security gadget, such as antivirus, intrusion detection sensors, etc., that we add to the system adds to the system footprint and adds to the system attack surface. These security features may actually provide the attacker with the way in that they're looking for. They might also provide the operator with a false sense of security. In both of these examples, characteristics of the trusted assured system cause the mission to fail. We must take into account the mission that we're trying to achieve, as well as the inevitable dynamics of emergencies and the fog of war. Back in 2003, the U.S. Department of Defense published DoD Instruction 8500.2, which defined mission assurance categories 1, 2, and 3. The categories define what's acceptable and unacceptable when information assurance characteristics are lost. Any loss of integrity or availability is unacceptable for Category 1 systems. Category 2 systems can tolerate some outages, but cannot afford the possibility of data corruption or loss of integrity. Finally, Category 3 systems can tolerate some loss of both integrity and availability. While assigning systems to categories in order to determine what protective measures might be appropriate is important, 8500.2 does not advise, beyond traditional information assurance measures, how to achieve mission assurance. Assigning things to categories and filling out checklists do not give us assurance. However, they can lead us to believe that operating the network or system is the mission, that complying with IA standards and regulations is the mission. Let me be clear. The network is not the mission. The system is not the mission. And finally, compliance is not the mission. These things must adapt to the mission. Finally, there are several constraints that we have to account for. Most times, we do not design and build the individual hardware components, infrastructure, or software components that make up our system. We do not define the communication standards or the protocols that must be used. Finally, we do not control the users and what they will do with the system, nor do we control the operators and what they will do with our system. These things are especially true in times of emergency and in contested environments, and this is critical to understanding why the traditional notion of information assurance is neither necessary nor sufficient for assuring the mission. By focusing on the mission instead of the system, the network, and achieving rigid compliance, we can create an approach to assurance that forces these things into a role secondary to the mission. They become responsive and adaptable to achieving the mission. In other words, the system is always functioning with just enough security to thwart the current threat or overcome the current emergency. The assurance features adjust to the environment at hand, or maybe present options that are appropriate to various conditions, including emergencies and situations where infrastructure is degraded, denied, or destroyed. Security compliance, and in fact security itself, may then not be necessary and is never sufficient by itself for achieving the mission. To accomplish this, the system must employ a layered architecture of features and services that rely on each other, but are at the same time independent. Designing mission-assured systems requires us to rethink assurance. The focus must be on risk rather than trust. Assessing risk demands a direct understanding of the threat and how it may impact the mission, whereas building in trust can be done haphazardly based on only inferences about the threat. Many times, trust is not even obtainable due to the constraints mentioned earlier. Designers do not control the hardware, software, standards, protocols, users, or operators of the system. As mentioned, assurance must be dynamic in order to adjust to a changing threat, changing environment, and unexpected use cases such as those that crop up in emergencies. Assurance must incorporate stochastic and redundant features that can be used when full knowledge of the adversary and their location, physically or logically, is unavailable. Finally, techniques such as obfuscation and disaggregation, characteristics not always welcome in traditional IA models, can be leveraged to maintain mission essential functions through disruptions. The layered architecture is key to the great success of the Internet. The original architects of TCP/IP networking knew that this approach was key to operation over a variety of different interconnected networks made up of a mishmash of components, some old, some new, some fast, some slow, and many error-prone. Layers request services from the layer below, and errors not corrected at a given layer are reported up to the layer above for possible recovery. Confidentiality, integrity, and authentication may be implemented at one or more layers, but no layer assumes anything about the others except for what gets passed between. Thinking about the nature of mission assurance I just described on the previous slides implies that security features at each of these layers must be responsive to the needs of the mission, the state of the threat, the connectivity environment, and the current use case. However, respecting the design philosophy of a layered architecture, we're not really allowed to start changing things and adding new services and features haphazardly throughout the stack. The answer? Let's add a new layer, layer 8, the mission layer. Layer 8, or the mission layer, achieves mission assurance by manipulating aspects of information assurance. The notion of pure trust changes to one of allowing risk only to whatever level is deemed acceptable to achieve the mission. The mission layer implements security with random characteristics because we never can assume we know everything about the threat. The mission layer facilitates not only protection of information, but also facilitates disaggregation, obfuscation, and redundancy. Now that we've discussed, albeit at a very high hand-wavy level, how we might implement mission assurance in networking through the addition of an 8th layer or mission layer to the 7-layer networking model, let me describe to you a case study that we undertook at the Information Directorate under the leadership of Dr. Kamal Jabbour, the U.S. Air Force's Senior Scientist for Information Assurance. The case study involves a radar site that feeds its raw data over a distant serial comms link to a display in a monitoring facility. Its mission is to provide the radar data to authorized users so that an accurate, up-to-date air picture can be formed. Some characteristics of the mission include the data is real-time. It has to be showing the air picture at any moment. However, it's short lifetime data. So after the track flies by, then we don't really worry about it too much. It's low bandwidth data. It's just the raw radar data coming across a serial line. And there are dedicated serial connections to the equipment at both ends. The major risks considered in the case study are first that there could be communication outages rendering the air picture out of date or non-existent. Man-in-the-middle attacks may inject false tracks or corrupt the air picture that the operator is seeing. The air picture data could be intercepted, giving unauthorized users a view of what the radar is generating. And finally, there's the fact that there's a single point of failure because of the dedicated comms link running between the radar and the monitoring site. Although this case study was not an attempt to address all aspects of mission assurance once and for all, we did strive to improve aspects related to some of the risks identified. Specifically, measures were taken to improve confidentiality to reduce the risk of intercept. We also addressed integrity and authentication to reduce risks related to unauthorized modification of the data in transit. Risks of outages and single point failures were addressed by including means of replication and redundancy. Finally, recognizing that the capabilities of an adversary can never fully be known beforehand, obfuscation and randomness features are included. This diagram shows the resulting high-level design concept. Source data is ingested at the mission layer, and the remaining 7 layers are called upon to encrypt using random keys and push obfuscated data over multiple redundant commercial communication channels into a large number of globally distributed cloud Dropboxes. Data is stored in the cloud for a finite amount of time and then automatically destroyed. On the destination side, the encrypted data is pulled from randomly selected Dropboxes, again over multiple redundant commercial lines, brute force decrypted, duplicates removed, and reconstructed. These functions are orchestrated by the mission layer and then passed to the destination system for display. We asked an independent organization to assess the improvements made by way of our network designed with an additional layer 8 requesting services from the 7 layers below. The assessment considered each strategy and gauged its effect on the tenets of information assurance. Although there is much still to be done, the results so far are encouraging. By taking into account the characteristics of the mission and the data, we were able to use the security services available in the network to improve the ability of the remote radar site to contribute to the success of the mission. Moreover, by challenging existing compliance requirements and traditional notions of confidentiality, integrity, and availability, we were able to realize a more resilient design that can operate through sudden disruptions and attacks. In closing, I hope I've stirred your creativity about assurance, what it is, what it's not, and what it could be. We must ensure that the systems we design and deploy achieve their purpose, even when subjected to unexpected conditions that fall outside the requirements and assumptions present during design. These include communication disruption, degradation, cyber attacks, and emergencies that thrust the system into use cases never envisioned or exceed original expectations. In fact, I would say if it's not about achieving the mission, then what's the point? We must devise technology that enables static information assurance to adapt and to give us mission assurance. A mission assurance model is driven by acceptable risk, not trust, partly out of necessity, as we cannot trust all the parts of our globally interconnected infrastructure, and partly because, with risk as a driver, it forces us to do a better job understanding the threat, which is key for achieving mission assurance. I described a very simple case study whereby we built an 8th layer of networking that considers the mission and then uses that consideration to request services as needed from the underlying layer. This simple example is not intended to show mission assurance how it should be implemented, but rather to showcase what types of things can be achieved with a mission assurance mindset. I hope that you'll take these thoughts forward into the workshop and beyond to figure out a way to design more robust systems that will work securely and satisfactorily when the environment is contested, degraded, and during emergencies. Finally, I wish to once again thank the workshop organizers and all of the participants that took time out of their busy schedules to watch the presentation and contribute to the discussions. I'm looking forward to meeting and interacting with you during the workshop. Have a great day.
My name is Suxin Yu. I'm here to present PrivyTRAC, Privacy and Security Preserving Contact Tracing System. First, motivation. In an epidemic such as COVID-19, tracing people who have come into contact with confirmed cases and therefore might be infected is one of the most effective ways to prevent isolated cases from becoming large-scale outbreaks. Traditional manual contact tracing methods through interviews are effective but very labor-intensive and too slow for fast-spreading diseases. Electronic location-based contact tracing methods, such as using smartphone locations, have proven to be an effective alternative to the traditional approach. They largely fall into two categories. The first is the centralized approach. The centralized approach aggregates smartphone locations in a centralized repository. When a confirmed case is identified, we can search a repository for anyone who had come into contact with the confirmed cases based on their cell phone location histories. The second category is a distributed approach. A well-known example is a system that Google and Apple have proposed. It uses Bluetooth radio to record all other cell phones in vicinity based on their Bluetooth signals. A user can then compare unique ID of confirmed cases to determine if they had come into contact with the patient. The smartphone location-based contact tracing has been implemented in various countries and proven to be effective. However, there are serious privacy and security concerns that have been raised. These concerns have limited widespread adoption of the very effective contact tracing methods. First, privacy. Aggregating personal information in a centralized location, regardless whether the person is ill or not, certainly raises privacy issues. Second, security. The centralized repository is an obvious security risk. Even for the distributed approach, individuals still record all of the people in their vicinity. Someone who is persistent and technically capable can aggregate data from multiple cell phones to start formulating the network of contacts and perhaps infer an individual's identity. Besides privacy and security concerns, the smartphone location-based approach relies on proximity to the infected person to evaluate the risk of infection. However, as we have known by now, viruses such as COVID-19 can linger on or travel in the environment for some time, especially when they exist in small droplets or aerosols. Therefore, proximity-based risk assessment may not give you a full picture to reliably assess risk. We propose a new smartphone contact tracing approach called PrivyTRAC. The system consists of two software components. One runs on users' cell phones and the other on a server. This slide shows the process and the information flow. Starting from the server software, location histories of confirmed cases are aggregated on the server. The server software computes a spatial temporal risk map. What the risk map tells you is a person's risk of infection if the person were at a particular location and particular time based on the movement histories of confirmed cases. The risk map is computed from processed location data from many patients and doesn't contain individually identifiable information. Hence, patient's privacy is protected. The spatial temporal risk map is uploaded to the cloud for the user apps to download. On the user side, once the risk map is downloaded, the app can compare the user's movement history on the cell phone to the risk map. The app automatically calculates the user's personal risk of infection. If the user has a high risk of infection, the app alerts the user and can also suggest locations for further testing. As you see on this slide, the information only flows one way, from the cloud to users. There's no information uploaded to the cloud or shared with other users. The feature is quite different from other smartphone-based contact tracing approaches in protecting users' privacy. Another useful feature that can be built into the server's software is to use the software as part of the planning and resource allocation tools. For example, for areas that pose higher risk, perhaps more resources should be allocated for disinfection. On the user side, the app can suggest people that are exposed to the virus to go to testing locations that balance convenience and demands for testing. This slide is a summary of benefits. We talk about how PrivyTRAC protects the privacy of both the patients and the users. Patients' privacy is preserved since the spatial temporal risk map only contains aggregated and processed location histories of the patients. Users' privacy is preserved as well, since no user information is shared in a centralized repository nor with other users. PrivyTRAC can also improve security, since it doesn't capture other users' information or aggregate them together. PrivyTRAC improves the accuracy of infection risk assessment instead of relying solely on proximity to the patients to determine risk. It also considers how long virus can linger in the environment and the accumulated risk from extended exposure. So, how do we actually create a spatial temporal risk map, and how do we compute a person's individual risk of infection? First, what is a spatial temporal risk map? The spatial temporal risk map quantifies the probability of contracting the disease at each location and time, per unit area and per unit time. If there are multiple patients in an area of interest, the risk map combines the effects of all of the patients and computes the total risk. The computation is done on the server side and updated when there's new patient information available. The first equation on the slide shows infection risk due to the presence of a patient at a particular location and time. As you can see from the equation, a location that is further away from the patient and/or time elapsed after the patient's presence, not surprisingly, the risk drops exponentially. If the patient moved around the area or there were other patients in the same area, we can aggregate the movement histories and calculate the total infection risk, which is the second equation on this slide. The infection risk map described on the previous slide is a three-dimensional spatial and temporal map that quantifies the risk of infection at each location and at a particular time. A user downloads the information to their app and determines their personal risk of infection by correlating their own movement history stored on their phone with the downloaded risk map. The second equation on the slide shows how the calculation is done. We conducted simulation experiments to compare PrivyTRAC with proximity-based risk evaluation methods. For the experiment, we consider a 100 meter by 100 meter area for a duration of 350 seconds. A patient enters the area from the left at time 0 and travels at the speed of 1 meter per second. The patient then exits the area on the right at time 100 seconds. A healthy individual enters the same area at random time, location, and speed. We repeated the experiment 20,000 times. Based on the simulated movement histories, PrivyTRAC declares that a person is suspected of infection if the person's risk exceeds a given threshold. If a higher threshold is chosen, then the false positive is low, but the true positive is low as well. Here, the true positive means that we correctly declare an infected person, while the false positive means that we mistakenly declare a healthy person as infected. We did the same analysis for proximity-based approach. We declared that a person is suspected of infection if the person is physically within a certain distance from a patient. Similarly, we can choose what the threshold distance is and change the true positive, and false positive probabilities. By varying the thresholds, we can plot the ROC curves as shown on the slide. The closer the curve to the upper left corner, the better. You can see that PrivyTRAC is significantly better than the proximity-only risk evaluation method. The difference of the two methods has a lot to do with how long the virus loses its virulence in the environment. We plot the ROC curves at 4 different sigma t. Here, smaller sigma t means that the virus' ability to infect decreases quickly after a patient leaves an area. For small sigma t on the right, on the left plot, not surprisingly, PrivyTRAC is fairly similar to the proximity-based approach. For larger sigma t, the two methods start to diverge. There are several directions we can extend the work. First, the current risk model does not consider environmental factors. Local prevailing wind can affect the direction of spread. Temperature and humidity can affect how long the virus survives in the environment. They can be incorporated into the model to improve its accuracy. The second research direction is to continually refine the local infection risk model based on test results of people who came into contact with patients. Whether the results are positive or negative, they both can be used to adjust the model parameters. In a paper, we presented a Bayesian probability approach to refine the risk model. Third, the software can be part of the planning tool. On the server side, the risk map provides advanced knowledge of where the resources may be needed. On the user side, the app can suggest testing locations that balance resource availability and user convenience. Thank you very much for your time.
Hello everyone, welcome to my presentation of my paper Formalizing Dynamic Behaviors of Smart Contract Workflow in Smart Healthcare Supply Chain. This paper has been accepted in the International Workshop on Security, Privacy and Trust for Emergency Events, EmergencyComm 2020. So my name is Mohammad Saidur Rahman and one of the author of this paper, and my other authors, the other authors of these papers are here. So let's start with the short outline of our paper. So these are the key topic that I will be presenting in this, I'll discuss in this presentation. So at first I will start with some motivation of the research. Then I will define the scope of the research. After that, I will give the overview of the proposed model, in which I will mainly discuss the colored petri net formalism for composite smart contracts and the smart contract composition logics. So later I will discuss about the experimental results, and finally I will finish with some concluding remarks. So basically the blockchain based supply chain management system uses blockchain and smart contracts. These two are actually two enabling technologies that ensure the traceability of products and prevent data tampering in the smart healthcare supply chain. In blockchain based supply chain, business rules are mainly abstracted as smart contracts, and they will be deployed in the blockchain networks to ensure that only to only execute the business logic that are compliant to this system or a particular transaction or something. Smart contracts validate blockchain transactions before they make any changes to the distributed ledger. So with this concept, we have some issue with this kind of blockchain-based supply chain system. Basically, a supply chain is a complex system. So if we want to perform any task in the supply chain, it will involve many participants in the system like producer, supplier, customer, distributor, and so on. So a workflow of smart contracts needs to be created, because a single smart flow will not be able to address all the problems, all the tasks in the supply chain. So we need to form a workflow of smart contracts. So this smart contract workflow will only be executed based on the input data. That means whenever we send a particular input data to the smart contract workflow, based on the data, it will identify the smart contracts and ensure the execution of the smart contracts. But so we can say that the smart contracts workflow is mainly data driven and dynamic. So we assume that we have a workflow, but how to ensure that the smart contracts are executing according to the input data? That means it is complying with the nature of the data. So it is necessary to verify the correctness of the dynamic execution of smart contracts. So we can consider a simple scenario. Assume that we have a payment smart contract between a supplier and a customer. Now, the payment smart contract will be processed only if the supplier sends X units of a pharmaceutical item to the customer. Now, assume that the supplier at first sends Y units to the customer and later Z units to the customer. So as Y unit is less than X, it is not equal to X. So the payment smart contract should not be processed. It should hold unless it gets another Z units, the remaining units of the contract. So we can say two different blockchain transactions will be generated for two different delivery, Y for Y units and Z units. And when these two different transactions will produce X units of delivery, then only payment smart contract should be processed. So this scenario should be modeled in a smart contract based system before the actual smart contract is deployed. Otherwise, the cost of smart contract execution will be wasted. So in this research, our scope is to develop a model that would verify the correctness of the execution of smart contracts with the dynamic behavior in the blockchain-based smart healthcare supply chain. We are using the healthcare scenario as our healthcare system as our scenario. However, it can be applied to any blockchain-based system. We will model a dynamic behaviors of a smart contract in a workflow-based workflow-based system on the business rules using colored PrivyTRAC. So mainly for the formalizing or modeling purpose, we are going to use a tool that is called colored PrivyTRAC. Colored PrivyTRAC is a version of the PrivyTRAC. PrivyTRAC is a very popular formalization method that is used for modeling different interaction among the components of a system. But CPNet or colored PrivyTRAC is basically model the dynamic behavior of entities. So we are going to use that one. CPNet is also being used to check the soundness of smart contracts in different blockchain-based system. So it is a common technique. However, recent or existing works does not consider the soundness verification of workflow in the blockchain-based system. So we are going to do that in this paper. The CPNet allows describing the smart contract behavior and logic through different tokens as colors. So we are not going to discuss the colored PrivyTRAC, the background of colored PrivyTRAC in details later. Rather, we are going to discuss the actual colored PrivyTRAC that we have model designed for our blockchain-based system. So before that, as an overview of the proposed model, smart contracts will take data in terms of transactions and pass data to the functions that implements the business rules. Each function will have one precondition and post condition that will be considered as guard conditions. Okay. So blockchain network should verify an input value of the guard condition before smart contracts are deployed on the blockchain. Complex supply chain tasks will require the composition of multiple smart contracts to execute all business rules. Smart contract composition may be performed based on the data that is provided in the transaction. So this is the overview of our proposed model. Now, let me introduce the composition logic that we have addressed and using this model. So we have 4 composition logic. First one is sequential, aggregation, split, and final one is loop. In sequential composition, let's say we have 2 smart contracts, SC and S prime. SC will send X unit to X SC prime. SC prime will only accept this value and execute the SC prime will only be executed if the value of X is equal to X or equal to X. But here the smart contract will accept any value that is less than X. So it will only execute if value of X and Y is equal, unless it will wait for the next values. So here, second one is the aggregation composition. Assume that we have 2 smart contracts, SC1 and SC2. SC1 sends X1 to SC prime and SC2 sends X2 to SC prime. So SC prime will only be executed if the summation of X1 and X2 is equal to Y. The split composition, in a split composition, a smart contract SC may invoke or call multiple smart contracts. So let's say a smart contract SC will send X1 to SC prime, SC1 prime, and X2 to SC2 prime. So if X1 equals Y1 and X2 equal to Y2, only then these 2 smart contracts will be executed. So in the loop composition, it is a series of sequential composition. So SC prime will only be executed if the total amount of Xi is equal to Y. So SC prime will wait for multiple input value unless it gets Y. So these are the 4 logics of the smart contract compositions. Now based on that, let's discuss the actual colored petri net formalism of the smart contracts. In this one, we have mainly defined smart contract net at first. This is the colored petri net for our model. Here we have this colored smart contract net or SCNet is a tuple of P, T, F, sigma, and C. Here P is the finite set of places in the colored petri net. We have different places, and these places are some can be internal places or data places. So assume that these data places will only be, these data places has some precondition and post condition. This is the source and sink places. On this will be only executed if this source and sink meets the criteria of the actual required data. So after that, we have several set of transitions. So T will be denoted as the set of finite transitions. So this petri net will only change the transition places if a certain condition is met. So F is actually some set of directed arcs presenting the flow of this smart contract. This sigma is the set of colored set. So in our model, there will be different colors. So this sigma will represent those set of colors. And C is the color function that will take different token to execute this function. After that, we have a smart contract. So a smart contract is again a tuple of different parameters, but mainly this consists of the smart contract net that you have defined previously. So I'm not going to discuss in detail. So the definitions are given here. So let's discuss the main thing that we are proposing here, the colored petri net formalism of smart contract composition logics. So based on our 4 composition logics, we have modeled the different colored petri nets. So in this is the sequential colored petri nets that will take a token from the smart contract SC1, and it will only be evaluated if the token can fulfill the requirements of the smart contract too. Similarly, we have modeled the aggregation smart contracts here, and then we have modeled the colored split composition, and this is the loop composition. So this is based on the colored patinate construct of any events. So you can see every smart contracts will have different places. Let's say this is the initial place and this is the end place of this smart contract, and these black boxes are actually events. So transition events, transition places. So after that, let's discuss the experimental results. We have implemented our model using Windows 10 operating system, using a Core i7 processor and 8 GB RAM computer. We have developed a Java-based application, and it has a server and client version. The server is designed using the Tomcat, Apache Tomcat. And we have considered 500 different smart contracts, and we have generated different number of workflow to evaluate the performance of our system. So here the first diagram shows the validation time for each workflow, proposed workflow, and for different numbers of workflow in this system. So let's say if we have a if our system has 25 workflow at a time, it will take around 2.5 seconds. If we have 50 workflow at a time, it will take around 7 seconds. And finally, if we have 100 workflow, it will take around 17 seconds to execute the system. So overall, it shows that the validation time increases exponentially, almost exponentially, if the number of simultaneous workflow increases. So in table 2, we are showing that the ability to check the correctness of our model. So when our number of workflow was 25, we found that 24 workflow was sound, it was working correctly, and one workflow was not sound. So here our correctness was 100%. Checking this correctness indicates the checking ability. So we knew that our system knew that this one workflow will not be able to work properly, so it correctly identified this one. We can see all of the scenario actually checks the soundness of workflows with 100% accuracy. So these are the experiment results. So this is the final concluding remark. Overview. As an overview, proposed smart contract workflow formalization model presents data-driven smart contract composition logics for the workflow. A formal model is proposed to analyze the correctness of a smart contract workflow before executing the actual blockchain network for different input data. It will actually benefits to minimize the cost of smart contract execution. Our experiment results demonstrate that the validation task can be performed efficiently for multiple simultaneous validation requests, and our formalism technique can also be used to capture dynamic behavior in any blockchain-based supply chain and other systems. So that's all from my side. Thanks for listening this presentation and watching this presentation. Thank you very much.
My name is Friedrich Doku, and I'll be talking to you about Khopesh, a secure contact tracing system. Khopesh's goal is to create an anonymous contact tracing system with strong privacy guarantees. By using Khopesh, users can send their reports to other users and the central authority without sacrificing privacy. We expect Khopesh to be used in a scenario where a government organization or a corporation would like to collect contact data on its employees or citizens. For example, the user Alice would like to send her contact data to the central authority, which could be a government organization or a corporation. She's able to do this without revealing her identity and who she has been in contact with. Furthermore, Alice can also send her data to her doctor securely without reviewing her contact data to the central authority or anyone else in the network. Deployment and threat model. We expect Khopesh's adversary to be a passive attacking adversary that observes all of its network traffic, controls all but one of its mixer servers, and controls an arbitrary number of users. The adversary's goals include figuring out who is in the network and who is sending reports to whom. Mixnet. Khopesh exploits a mixnet in order to provide users with sender anonymity. If you don't know already how a mixnet works, essentially users encrypt their reports using each public key of each mixer server. Mixer servers are pretty much proxy servers, and the mixnet itself is a chain of these proxy servers. So once a user has onion encrypted his reports, what he will do is that he'll send it to the mixnet, and each mixer in the mixnet will decrypt the layer of encryption before sending it to the next mixer. Right after decrypting, the mixer that receives the messages right after decrypting, the mixer will shuffle the messages and send them out in random order to the next mixer. Once the last mixer receives the messages, it will shuffle them again, but then it will output them to its actual destination. Khopesh overview. In Khopesh, users authenticate themselves by using their cell phones. Once authentication is complete, this server right here, the public key generator, will send Alice and Bob their IDs. We will explain identity-based encryption and private key generators in the next couple slides. Anyways, once Alice comes in contact with Bob, she adds him to her contact data. And once Alice gets infected, she alerts the central authority. So what she does is that she onion encrypts her contact data. This will contain contact data is all the people that Alice has been in contact with. This will be unknown to the central authority. We'll get to that sooner or later. Once she has encrypted her contact data with the public key of the central authority, she'll encrypt her data again, onion encrypting it with each public key of each mixer in the mixnet. After that, she'll send it to the mixnet. The mixers will remove their layers of encryption and send the contact data to the central authority. Once the central authority removes the last layer of encryption, it puts it in a report mailbox. There are two different mailboxes in Khopesh, one for reports and another group of mailboxes that users use to send reports between each other. At the end of every round, users will download the report mailbox to see if any of the people they have been in contact with have been infected with the virus. Khopesh's mixnet differs from traditional mixnets. For example, Khopesh implements mixed minions timed dynamic batching strategy. This protects Khopesh's mixnet from N-1 attacks. Furthermore, Khopesh is not vulnerable to one type of active attack, unlike regular mixnets. For example, we have two adversaries that have taken control of the mixer nodes. This means that they can, instead of shuffling the messages, they can output it in any order that they want. This makes it easier for the adversary to figure out who is sending messages to whom, thus breaking our sender anonymity. To stop this, what we do is we use verifiable shuffles. Each mixer shuffles the messages, and then all the other mixers in the network have to verify that a mixer shuffled the messages. These proofs are necessary to make sure that each mixer is behaving properly. Furthermore, these proofs are also zero knowledge, so other mixers in the network won't need to view the reports to see whether or not a mixer shuffled them or not. The private key generator. This is what I was talking about earlier. This is what users use to authenticate themselves. What would happen is that a user requests to join Khopesh, so the private key generator will send the user a unique code to her cell phone. When she receives the code, she'll send it back to the public private key generator. Once the private key generator receives the code, he will send the user a unique ID. In most cases, private key generators are used for creating private keys for each user. But in this case, in Khopesh, private keys aren't created for users, they are created for groups of users. We'll get to that soon. This is what I was talking about when I said private keys were created for groups of users. To communicate in Khopesh, users use shared private keys and shared public keys. Since private key generators utilize identity-based encryption, the public key is nothing more but a string. Okay, for example, let's say that Bob, Charlie, and David decide that they want to be able to monitor each other's infection reports. So they each add their phone number to a secure contact contract and send it to a PKG. A secure contact contract is what enables users to communicate between each other. So Bob, Charlie, and David authenticate themselves with the PKG and receive a copy of the secure contact contract that they will agree to. All users must agree to the contract. If one user disagrees, then the contract is invalid, and no keys or ID will be created. Okay, if they all agree, then they will receive a shared ID that they will be used to encrypt their messages using identity-based encryption. And they will also receive a shared private key that they will use to decrypt each other's messages. Users in Khopesh collect data when they come in close contact with each other. This is made possible by using Bluetooth. So what would happen is that users advertise themselves as Khopesh users. And once they discover each other, they exchange contact data. Contact data is organized in a tree data structure. The root node is the user. As you can see, there are no names in the tree. There are only unique identifiers that are created by the private key generator. This is Alice's data. And these are people that she's been in contact with. The first two people right here, the hash J85LD8FK and D7G9ZZQT, are people that she's been in direct contact with. Unlike the other two over here, these are indirect connections. The reason that Khopesh includes these indirect connections is because later on, when Alice downloads the report mailbox, she might find out that one of her indirect connections have been infected. This probably means that her direct connection has been infected, and that there could be a chance that she has been infected as well. This makes it a lot easier to keep track of who has been in contact with whom. And as the depth increases and you get lower and lower down the tree, the probability of Alice being infected with the virus also decreases. The higher up the tree, the probability increases. Implementation setup. So we ran Khopesh using 9 servers on DigitalOcean. Each server ran an Intel Xeon Skylake 2.7 GHz CPU with 4 cores, 8 GB of RAM, and 1 GB per second of network bandwidth. Each server was running Linux version 5.7.7. We did not use cell phones for users. Users were simulated, and each user had a pre-made report of 1,192 bytes. We ran with 3 mixer servers, 1 private key generator, a central authority, and 4 client runners. These client runners are responsible for simulating the servers. What we do is always split it up between servers and we run clients in parallel. All of this was implemented in roughly 4,000 lines of C++. Scalability. So, for contact tracing, latency is a little bit more lenient. The constraints aren't like instant messaging. As long as users are able to be notified in a reasonable amount of time, then that's all that matters. Using our limited amount of resources, we're able to run 10,000 users with an end-to-end latency of roughly 130 seconds. As you can see, Khopesh linearly scales. Limitations. Using Bluetooth to detect other users can lead to an increased number of false positives because the distance between users is not very accurate. To solve this problem, we could use Bluetooth localization techniques. Verifiable shuffling. Khopesh implements a verifiable shuffle algorithm which takes 2 minutes to prove and verify 100,000 reports. That seems like a reasonable amount of time for Khopesh, but this current implementation does not exploit parallelism. So there are many cores that are just being left that aren't even being used that could be exploited. So to make sure that we're using all the resources that we can use efficiently, it would be better to implement this verifiable shuffle algorithm in parallel using OpenMP. Forward secrecy. Khopesh's current design does not include forward secrecy. This means that an adversary could be downloading the reports from these mailboxes. Since these mailboxes are public memory locations in the central authority, then adversaries will be able to download these reports every round. And once an adversary is able to discover a key, then she'll be able to decrypt each report. However, these reports don't really tell you much about an adversary, since the only thing that is included in these reports are unique IDs. Contributions. Analyze the design of Khopesh, a secure contact tracing system that keeps its users anonymous and their contacts protected. What we've also done is that we introduced a novel technique called secure contact signing, which allows users to form groups and share their reports securely.
So we have come to an end to this workshop today. We really would like to thank again to all of you for your time, and we are really grateful to all of you for your kind participation. Lastly, we really again look forward to keep hosting this workshop in the next years, and we look forward for your participation again. Thank you so much, and enjoy your day.